rational functions today. A rational function is a function with a fraction. Okay? It's going to look like this. You're going to have a polynomial in the numerator and a polynomial in the denominator. Okay? You need to simplify if you can, which means it's going to be to your benefit to simplify the numerator and the denominator and see if you have any factors that cancel. Today we will talk about what happens when factors cancel, okay? But before you go to graph it, it has to be simplified. That is your first step, okay? Your domain is going to be all real numbers except the x values that make the denominator 0. That's something that we've done before. Okay, I don't think that's something that you need to write down again because we've already talked about the domain of rational functions. Okay, biggest thing, we have to simplify first if we can. Okay. Now, when we have a rational function, we have the possibility of having vertical asymptotes. How do we know where to find a vertical asymptote? Turn to your neighbor, make a guess. How do we know where the vertical asymptotes are? All right, back up here. How do we know where an asymptote is? A vertical asymptote. Nobody? What number can we not divide by?
0.
0. If we divide by 0, we have an undefined value. If we divide by 0, that is where our asymptotes will occur. Okay, so a vertical asymptote is a vertical kind of, I don't want to say imaginary, but like if you graph these in your graphing calculator, you're not going to see the asymptote. It's just implied that it's there. We draw them in with little dotted lines, right? But we have an asymptote, and on either side of the asymptote, our curve is going to either approach it towards infinity or negative infinity. Okay? Depending on the curve, both might go the same way, and that is not a problem. Okay? But as we get closer to the asymptote, we are going to approach it, but never touch it. If we have horizontal asymptotes, okay, if we have vertical asymptotes, it is also a possibility for us to have horizontal asymptotes. We've had sort of a small conversation about the asymptote rules, but we need to talk about them for real because now we're going to really need to know them. Okay? So first of all, a horizontal asymptote is a horizontal line, and it means towards infinity or towards negative infinity. Whoops. Our curve is going to approach that asymptote. It is okay to cross a horizontal asymptote. If you remember back to some of your problems last year, you might have had something that looked like this. Can I remember that? It's okay to cross the horizontal asymptote, like kind of towards the middle of the graph, as long as towards the ends of the graph we approach the asymptote. So now we need to talk about the rules. Okay? There are 3 rules. There's a rule for when we identify horizontal asymptotes, we need to compare the degrees of numerators and denominators. Okay? So we have a rule for if the denominator has a higher degree. We have a rule for if the numerator and denominator have the same degree. And then we have a rule for when the denominator has a smaller degree. Okay? So our first rule, if the denominator has a larger degree, where's our horizontal asymptote? 0. Say with confidence. If our numerator has a smaller degree than the denominator, our horizontal asymptote is y equals 0. Okay, guys, I was starting to panic. I thought we only had like 1 minute until lunch started, but it's Wednesday. I have some more time. Okay. Where did all of our time go? Okay. Turn to your neighbor and see if you can remember the rule for when numerator and denominator have the same degree. Kind of quiet, so that makes me nervous. Will, do you remember? No. Okay, let's go on French. Connor? Do you remember? No. Henry?
Yes.
You remember?
No.
No?
Not on the slightest, I'll be honest.
Anybody? Really? If degrees of numerator and denominator are the same, then we look at the leading coefficients, and it's y equals whatever those leading coefficients are, a over b, or whatever. Okay. Does that sound familiar now that I say it? No? Still?
Yeah, because like when we did that, probably just the words that
Okay. Please keep in mind that when we do examples, things make a little bit more sense, right? Okay. So if the degrees are the same, we look at the leading coefficients, okay, which our first example, we'll see that, okay? And then if the numerator has a larger degree, okay, that means the numerator is bigger than the denominator, right? Okay. In that case, we do not have a horizontal asymptote. And this is the case that you just kind of ignored last year in Algebra 2, if that's what you took last year. But now we're going to actually talk about it, okay? What happens is we actually have what's called an oblique asymptote, and we are going to look at graphs that have slant asymptotes. And they're going to be blue.
Is that something that we need to like write down?
We will write it down in a little bit. Okay, so in order to graph these, to graph our rational function, first thing I told you had to do was what? Simplify. Okay, From there, you are going to identify and sketch all of your asymptotes. You're going to identify your vertical asymptote, sketch them in. You're going to identify your horizontal asymptote, sketch it in. Okay. You need to plot at least 2 points. I'm going to say per branch. And I know that sounds kind of weird. We're not graphing trees, okay? But you know that when we have all of these asymptotes breaking up our graph, we kind of have these pieces, different pieces. So for each piece, I need at least 2 points so you can get the shape, okay? So you may want to make like an XY table off to the side to get all of your little pieces, okay? Make sure when you draw these pieces, you're going to draw smooth pieces, okay? All of these are smooth curves. They're not jagged. They're not pointy. They're not linear. Okay, they're all smooth. So this is my plan. We're going to try to get through an example before we go to lunch. And then we'll have 2 examples for after lunch. Are you ready? Okay. Please write down our first example. 2x squared over x squared minus 1. It is a fraction. So therefore it is a rational function. Can we do any sort of factoring? In the numerator? No, we only have one term. In the denominator? Yes. That is your first step. Factor. And then see if you can simplify. Can we simplify? We cannot. But this factoring helps us identify our asymptotes. Okay? Connor, I'm going to come back to you. Where is the denominator 0? At -1 and +1. So we have vertical asymptotes at x equals -1 and x equals +1. Notice how I'm emphasizing x equals and x equals. They are lines. Please write them as so. Okay? So I'm going to come down here and I'm going to draw in my vertical asymptotes. Okay, I'm going to count by 1/2. Okay, just so you can, it's not so squished. Okay. What is true about the degree of the numerator compared to the degree of the denominator? They're the same. So what we do, I know some of you are kind of panicking, we look at the leading coefficients. The leading coefficients are 2 and 1. We keep the fraction bar in between. So 2 divided by 1 is our horizontal asymptote. And let's go ahead and draw that in. At this point, we know what our domain is, okay? We don't have to look at the graph to figure out our domain, okay? Our domain. Go ahead and write down what you think the domain is and compare it to your neighbor. Nope, interval notation. Finn and Ryan? What's our doing?
Negative infinity to negative 1, and those are both in parentheses.
Mhm.
1 to infinity in parentheses.
Okay. I like both of those. Can we have numbers between negative 1 and 1?
Yeah.
Yes. So we also need the interval negative 1 to 1. So we have negative infinity to negative 1, negative 1 to positive 1, positive 1 to infinity. So this is all real numbers except for those asymptotes. Okay? So now we get to come down here and draw in our curve. Your asymptotes, your vertical asymptotes, have broken this graph up into 3 different pieces. Let's just pick a side of the asymptote to start with. So we have an asymptote at x equals 1. To the right of 1, a nice number to plug in would be 2. When we plug in 2 to 2x squared over x squared minus 1, what do we get? What do we get? 8/3. So at 2, you're at 8/3. What about, let's plug in one more. What about when we plug in 3? Nine fourths. Okay, so now that we have 2 points for that piece, we know that it's going to approach the horizontal asymptote and approach the vertical asymptote. Okay? Pick a new piece to work on. Since we just did to the right of 1, let's go over here to the extreme left side of our graph, and let's go to the left of negative 1. Nice numbers to plug in there would be negative 2 and negative 3. What happens, Gabe? Oh, what'd you say? What'd you say?
So you're gonna see a pattern.
We are going to see a pattern. What happens when we plug in negative 2?
It's the same as when it's negative u squared.
Uh-huh. We're going to get 8/3 and 9/4 again because that square is going to basically take away the negatives, right? Okay. Now I will tell you that in between your 2 asymptotes, anytime you have double vertical asymptotes, there is either going to be a U or it's going to snake through and cross the horizontal asymptote. Okay? In order to figure out if it's a U or it snakes all the way through, you are going to have to pick 3 points in between there. Okay? That way you can get an idea of what is happening. Okay? Since we are so close to lunch, I'm just going to tell you, when you plug in 0, you get 0. When you plug in 1/2, you get negative 2/3. And when you plug in negative 1/2, you get negative 2/3. So what's happening is we have a U. When we get back from lunch, we'll talk about what the range is. So when you get back from lunch, maybe write down what you think the range is. And then we're going to go through an example with a hole. And then we're going to go through an example with a slant asymptote. Hustle back when you are done. All right, I hear a lot of great conversations about the range. Pod 7, what did you discuss?
We said negative infinity and 0 with the bracket, and like the U thing, and then to infinity.
Okay, so negative infinity to 0, and then 2 to infinity. How do you feel about that? Sounds pretty good to me. I like that Darby said that we needed a bracket with 0 because we have a coordinate at 0, it needs to be included. But then since we don't actually cross the horizontal asymptote, we would need a parentheses from 2 to infinity because it never touches the y value of 2. Okay, so there's your range. If we were to have the case where this squiggled through, like that one that I kind of roughly drew on the board, what would that range be? It would be all real numbers, okay, because it would stretch all the way through. Yeah.
How can you have something that crosses an asymptote?
Horizontal asymptotes are okay to cross because the definition is only that we approach them towards the infinities. So it's okay to have a function cross it like somewhere in the middle as long as towards the infinities it approaches. Okay? Kind of awkward. Vertical asymptotes we will never cross, but horizontal asymptotes it is okay for that to happen. Okay? All right, let's do another example. When you write this down, you know our first step is to simplify. So go ahead and write it down and then factor the numerator and factor the denominator. That way we can decide if this can be simplified. Here's what I got for my factoring. Do you agree? Okay. Can we simplify? We can. We can simplify by crossing out the x plus 2 factors, which means we have x minus 1 over x minus 3. That's the graph we're going to see. However, since we crossed out the x plus 2 factors, -2 still makes our denominator 0, which is not okay. But since the factors crossed out, we don't have a vertical asymptote there. We have a hole at x equals -2. Anytime you cross out factors to simplify, you will get a hole in your graph. Because we have an undefined value, we can't divide by 0, but we don't have a vertical asymptote. Okay? So we're going to look at this simplified function. Okay? Caroline, where is our vertical asymptote?
3.
Good. X equals 3 is our vertical asymptote. Okay? The degree of our numerator compared to the degree of our denominator. Oh. Would I do that? There we go. Same, bigger, smaller. Same. Okay. So Gabe, what's our horizontal asymptote? Okay, we have 1 over 1. So y equals 1 is our horizontal asymptote. Okay, so I'm going to go ahead and draw those in. We have x equals 3 and y equals 1. Okay, the domain we can always identify before we graph it. The range, typically we want to wait till the end. Okay, so our domain, we have to look at our original function. There are 2 places where the denominator is 0, so both of those have to be excluded. I know we simplified down to here, but when we're looking at where our original has a denominator of 0, that's what we have to consider for domain. So our domain is negative infinity to negative 2, negative 2 to 3, and 3 to infinity. We have to exclude both negative 2 and positive 3. So now let's go to the graph. The easiest way to do this is to just pick nice values to plug in on the right side of your asymptote. Draw that piece. Pick nice values on the left side. Draw that piece. So what are a couple of nice values to the right of 3? 4. Now choose 5. What the heck? Okay. When we plug in 4, okay, we did some simplifying. Please use that to your advantage. Plug into here. When we plug in 4 to x minus 1 over x minus 3, what do we get? And when we plug in 5 to x minus 1 over x minus 3? Okay, so we have 2 points. We can go ahead and draw in our curves. This. I miscounted maybe a little bit. 1, 2, 3. 1, 2. Is that better? I think I counted from my asymptote instead of the x-axis. Thank you, Gabe. Okay. Let's go to the other side. What are a couple nice values for us to pick on the left side? What? 2. 1. Right? When we plug in 2 to x minus 1 over x minus 3. When we plug in 1 to x minus 1 over x minus 3. What was that? 0? Okay. Now don't get too excited with your curve, because what did we say? We are going to have a hole at x equals negative 2. Okay. So what we need to do is we need to plug in negative 2 to our simplified function to see where that hole is. When we plug in negative 2 to the x minus 1 over x minus 3, what do we get? 3/5. So at negative 2, 3/5, you're just going to draw an open circle, and you're going to connect those points. Okay. So it looks like the graph x minus 1 over x minus 3, except we have a hole at negative 2, 3/5, because we had those factors cancel out. Okay. Any questions about that hole? It's actually kind of nice, right? We got to simplify, so plugging in values was a lot easier, right? Okay. All right, let's go back and talk about our range. What y values are not included in our range? Turn to your neighbor and decide which y values are not included in our range. Okay, what do you think? Jackson.
You said it would be all values except for 3/5 and 1.
Okay, we do not have a y value at 3/5, because that's where the hole is. We do not have a y value at 1, because that's where our horizontal asymptote is. So our range is negative infinity to 3/5, 3/5 to 1, and 1 to infinity. We have to exclude the asymptote, and we have to exclude the hole. Okay. Do you see why waiting till we have it graphed is a better option for identifying the range? Okay, we don't know where that hole is until we graph it, all right? So I would wait till the end to identify your range.
So, why can you not have one at 1 if you can cross horizontal asymptotes?
It's possible to cross horizontal asymptotes, but that doesn't mean it will happen. So since we graphed this and it did not cross the asymptote, we exclude it from our range.
So if it happened to, then it wouldn't.
Correct.
Okay.
Correct. Really, the only time you're going to see it cross is if you have 2 vertical asymptotes, and still then not all the time.
Okay. So then, like, what are horizontal asymptotes? Like any line may or may not be crossed in a function.
Well, a horizontal asymptote just tells us that towards infinity it has to approach that asymptote, and towards negative infinity it's going to approach but not cross it. What happens in the middle can be kind of whatever, but towards infinities it's going to approach it. Does that make sense? Okay. Let's now talk about that third case. It's fun, right? When we have the degree of the numerator exactly 1 more than the degree of the denominator, we get what's called a slant asymptote. Okay? A slant asymptote. It's basically going to be a line with slope. Slant. Okay? A line with slope is going to be our asymptote instead of a horizontal asymptote. Okay? When the degree of the numerator is exactly 1 more than the degree of the denominator, to find that line, we get to use division. If the numerator has a higher degree, it means it's larger, okay? Which means we can divide by the denominator, and that's what we're going to do. We're going to take the numerator divided by the denominator, and whatever the quotient is our asymptote. Remember, the quotient does not include the remainder, so we don't really care what our remainder is. We just want the quotient, okay? So our numerator is going to be exactly 1 more than the denominator. Since it's a higher degree, it's larger, which means we can divide numerator divided by denominator. When you do that, the quotient is your slant asymptote. Okay? This is why this section is in this chapter. It seems kind of random. We've been talking about polynomials, and all of a sudden we have these asymptotes, right? It's kind of weird. It's in this chapter because we need that division piece that we've been working on to find our slant asymptotes. Okay? Now, you can use long or synthetic division, but synthetic division only works sometimes, so you'll have to make that decision when you get to the problem. Okay? Are we ready? Here we go. X squared minus x over x plus 1. What is your first step? Always. See if you can simplify. That should include factoring both the numerator and denominator if you can. Cool. Can we simplify? Can we simplify? No. It's worth a try. Okay, so now let's look at where our denominator is 0. Our vertical asymptote is where? X equals -1. Since the degree of our numerator is 1 more than the degree of the denominator, we are going to use division to find our slant asymptote. You can use long division or you can use synthetic division. It does not matter. What would you like to do? If we can do synthetic, we might as well. Please keep in mind that our numerator is 1x squared minus 1x plus 0. And what is our k value for out here? -1, because x plus 1 is our divisor. Okay? So, when we do synthetic division, we drop the 1, multiply to get -2. Oh, nope, I'm a step ahead of myself. Multiply to get -1 to add to get -2. It does not matter what your remainder is. It can be 0, it can be 1500. It does not matter what it is. We don't need it. Our quotient is at x minus 2, which means y equals x minus 2 is our slant asymptote. Write down your quotient, set it equal to y. You should have a linear equation. It should be a line. Because we're only doing this with when the numerator is 1 more degree and then when the numerator is 1 more degree than the denominator. So we should have a linear quotient. Okay? Graphing a line. You probably miss graphing lines, right? What once seemed maybe difficult seems so easy now, right? So x minus 2, we have a y-intercept of -2 and a slope of +1. Okay? This might be a time you want to use your new ID card to help you. Right? You guys got your IDs today? Okay? There's our asymptote. Okay? Looks pretty funky, right? Okay? Don't let it intimidate you. We're still going to pick values the same way. We're still going to pick 2 values on the right side of our asymptote, so 0 and 1. And we're going to pick 2 values on the left side of our asymptote, so -2 and -3. Okay? So, help me out. When we plug in 0, what do we get? We get 0. When we plug in 1, we get 0 again? Okay. Well, we know that it probably isn't just like constant between there. We know that it has to approach this asymptote, so it probably like turns in between those. Oh, it turns and then approaches this asymptote. It's not going to cross either one of them. Okay? What do we get when we plug in -2? -6. 1, 2, 3, 4, 5, 6. I have a guess as to what -3 is going to be. -6. Okay, got a little symmetry there. And there's that curve. Okay. I am never going to ask you to identify the range of a graph with a slant asymptote. We don't exactly know where those curves are switching directions. Okay, so we know that our range would be from -infinity to here and here to infinity, but we don't know what those y values are. We're not going to worry about it. Yay, one less thing to do. Okay, but I will ask you for the domain. Okay. Will, what's our domain?
-infinity to -1.
Mhm.
And then -1 to
What do you think? Do we have any more values to exclude? What makes our denominator 0?
-1.
-1. And that's it, right?
Yeah.
That's the only thing we have to worry about. On our other two examples, we had 2 values that made our denominator 0, so we had to exclude both of them. In this one, we only had 1 value that made our denominator 0, so we only have to exclude that 1. Okay? So here's the deal. What is new to you this year? You never saw a graph with a hole. You never saw a graph with a slant asymptote. You've seen other graphs with some with 1 vertical asymptote, some with 2 vertical asymptotes. Since the hole and the slant asymptote, since those are 2 new topics, what do you think I'm going to ask you on quizzes and tests? Probably a graph that has a hole or a graph with a slant asymptote. Okay? So make sure that you are comfortable working with those kinds of graphs. Okay? This is your homework. It's on your gold sheet. Okay? What I'm going to do in the first few minutes of class tomorrow, I will show each of the graphs up here on my board. If you have an odd problem, check your graph in the back of the book. But then if it's an even problem, know that I will show you what the graph looks like tomorrow. Okay? And we can talk about anything that we need to. Okay? Let me stop this recording really fast.